be static, so I think we can start in. So welcome everyone, both our RASC Ottawa members, our guests in Ottawa who are non-members, which we're welcome to have with us, and any members from other RASC centers across the country. Glad to have you all in the meeting. If you're surprised, for most of you who know me, to hear me speaking right now, our meeting chair, Mick, caught me by surprise an hour ago with a nice email saying, I don't feel so good. I'm going to bed. Have a good evening. So at the last minute, I've discovered that I'm the meeting chair tonight. So bear with me while I try to do his job without trying to duplicate his Australian perspective on things. I wouldn't dare try that. Just some opening standard remarks we make at the beginning of every one of these meetings. We're obviously using the Zoom webinar format. We use that format very intentionally to reduce the chance of anything nefarious happening from outside sources. This is recorded, and I'm going to stop my comments right there because I forgot to start the record button. This meeting is now being recorded. Sorry about that. And the recording of this will be available on the website once Mick is feeling better and has a chance to process it. While our speakers are making their presentations, feel free to pose questions to them. Please do it through the Q&A function, and we will monitor your questions and then relay them to the speaker at the appropriate time, either during their talk or at the end of it. You're free to use the chat box to chat back and forth between people, but we don't always promise to see embedded questions in chat for the speaker, so try to use the Q&A. If you're a panelist, you'll have to use the chat box if you want to pose a question. We'll try to find it. And lastly, the raise your hand function of a webinar is disabled, so we'll get to your comments through the Q&A and the chat room. So moving along, here's our agenda for this evening. I'm pretending to be Mick and giving the introduction here. We have our standard opening chapter we always like and enjoy from Dave Chisholm of What's on the Skies for August. And then a special guest speaker, Dr. Robyn Fiori, who some of you will recognize her name, and you'll certainly recognize her as she presents. We've had her once before in 2018, and she's back with a second chapter of the impact of space weather on us. Mick, unfortunately, had a presentation he was going to make tonight. He even had it ready last month, and he bumped himself in favor of a last-minute talk by Jesse Rogerson on the new imaging from the James Webb Space Telescope. He was really looking forward to making this presentation tonight. The title makes it sound serious. It might not have been so serious, and it might have had an Australian flavor to it, but I won't spoil any more, and hopefully we'll get that next month. But he has, of course, posted his AstroTrivia and even put it on the web for those who wanted to research it in advance. We'll cover that during the break. And then we're pleased to have Rick back for his second segment on the RASC Astro-Imaging certificates. You remember last time he did the first one on deep sky objects. And tonight he's dealing with solar system certificates. We've got lots of observations from people, and of course the observing challenges from Oscar. A few other introductory comments. Welcome to 4 new members, Chris, Katie, Mark, and Victoria, who've joined us in the last month. So joining a group of 34 new members in 2002. So welcome, and hopefully some of you are here with us tonight. Looking at members in the news, we have one item this month, and that is Marcus Leach, a well-known member who likes to speak on his favorite subject of radio astronomy. And here's coverage in the local newspapers in the west end of Ottawa, the Carp, Stittsville, Canada area, highlighting the work that Marcus and his Canadian Centre for Experimental Radio Astronomy are doing. In particular, that they've taken on a new task of repurposing the large dish that's at the Diefenbunker and hoping to use it to do radio astronomy on colliding black holes. So ambitious, challenging new project, and best wishes to them for that. And for people who are not members or new and joining and watching with us, just to let you know, you're welcome here as non-members, but membership in the RASC in the Ottawa Centre is obviously available in different pricing, whether it's for an individual person, a family with additional members that then pay less than multiple times the regular, and a discounted price for youth members. And in return for that membership, not only, of course, do you join these meetings, but you have extra benefits that non-members don't have, such as access to our Fred Lossing Observatory in the Almont area and all of its telescopes and facilities. The RASC observing certificates you see there with the M symbol representing the Messier certificate, which you'll hear more about tonight from Rick. And if it wasn't for COVID, and if we were meeting as we would like to do at the Aviation Museum, we would have our telescope loan library and our book library, but unfortunately not during COVID yet. And in addition, with membership, you also get these 4 publications. I think just the publications alone more than justify the overall price of membership. But you get the Sky News put out by the RASC nationally across Canada every 2 months, the RASC Journal, a more scientific oriented publication, the annual Observer's Handbook, as well as our great monthly newsletter, Astronauts, put together by Gordon Webster. And as Mick would like to say, and more important than all of those, the camaraderie and the great assistance and learning that you get from working with all of the members, whether it's through these meetings or out in public observing and public star parties and through our members' emails list. So with that over, let's move to our first talk and our standard segment by Dave Chisholm on Ottawa skies for August. So go ahead, Dave.
Okay, thank you very much. So let's see what's happening in the Ottawa skies. First of all, let's take a look at the moon phases. So you can see I've highlighted tonight, we got basically a half moon. As you know, most of you are aware, we have the Perseid meteor showers. And let me see, they occur on August the 12th. What's on August the 12th? Full moon, super moon. It's going to wash them out. So best to be looking at those probably before the full moon, because they're going to be washed out. This full moon was known by the early indigenous peoples as the sturgeon moon, because large sturgeon fish of the Great Lakes and other major lakes are more easily caught at this time of the year. It's also been known as the green corn moon and the grain moon. This is the last of the 3 supermoons for 2022. The moon will be near its closest approach to Earth and may look slightly larger and brighter than usual. Frankly, I haven't really noticed the difference between a regular full moon and a supermoon, but anyways, that is the case. Talking about the Perseid meteor showers. So we have the Perseid meteor showers peaking on the 12th and the 13th to coincide with the full moon. It's one of the best meteor showers, up to 60 meteors per hour. It was produced by the comet leftovers from the comet Swift-Tuttle, discovered in 1862. It runs annually from July 17th to August 24th. So you're anytime in that range, you're welcome to go out and see if you can spot them. And they appear to be radiating from Perseus, just above Perseus. There, you can see it on the picture. Sun, we can see the days are getting shorter. We're going to get our telescopes out a little bit earlier every evening, which is great. Don't have to stay up quite so late. Mercury. So we've got the greatest eastern elongation on August the 27th. That means that it's furthest separated from the sun. So the best time to view Mercury would be in the evening sky just after sunset. It'll be quite clear. And you'll be able to see it either side of that date as well. But that's the peak date is August the 27th. Venus is visible in the morning, first half of the month. And Mars is visible in the late evening and through the night. By the end of the month, you'll be able to see it at 11:15. So, well, at least it's at the horizon at 11:15. So probably a half hour after that. Jupiter is moving into good viewing times in the evening sky. Right now, it's 11:45. Well, add a half hour to that. This is the horizon times, obviously. By the end of the month, it'll be quite easy to see in the evening sky. And similarly for the next one, which is Saturn. Saturn's even a little bit earlier, and it's that opposition closest to the Earth on August the 14th. Uranus is visible in the evening and through the night, as is Neptune. And isn't this true? That's my cartoon of the month. So thank you, Chris.
Thank you, Dave. I was really wishing you'd do a better job of organizing the Perseids on some other date than the full moon.
I'll try next year. Let's see how see how the moon lines up next year.
I have the fun job of doing a public astronomy session on August 12th, advertises the Perseids without low horizon. So I'll have no planets, full moon, and not many Perseids. So,
oh well.
Oh well. Moving on, real welcome to Dr. Robyn Fiori. As I mentioned earlier briefly, some of you I'm sure will remember, she joined us in 2018. I think it was in our May meeting on her favorite subject in her profession in dealing with space weather. And at that time, her talk was really focused on the impact of aurora on the Earth. So tonight we hear a different side of space weather and its impact on satellites. So as you can read here, Robyn is a scientist with Natural Resources Canada, dealing on a very different side of weather than we normally think of. We normally seem to care about what's sort of from the cloud level and below, and she's dealing with a much broader impact of weather. So without further ado, welcome, Robyn. I will stop sharing my screen so that you can share your screen.
Perfect. I'll give that a try. Okay, you should be able to see my presentation in just a moment. Let me know when that's up.
Yes, we can now see it.
Okay,
yep.
Perfect. Okay, thank you for the introduction, and thank you so much for inviting me back. It is always nice to speak to an audience that's genuinely interested in the topic. I think space weather is amazing, and I like to be exposed to some of the work that you do as well, so it's a really nice time to get together. So I am with the Canadian Space Weather Forecast Centre, which is really a part of the Canadian Hazards Information Service within NRCan. So CHIS, which is what we call ourselves, also looks at a lot of other different types of natural hazards, landslides, earthquakes, seismic activity. There's also a nuclear emergency response group, and then of course space weather. So it's a really wide range of topics, but the idea is to be able to look at information on natural hazards and then provide information to Canadians about those hazards and how we can avoid them if possible. Now, space weather is very interesting to me. It's a hazard that we like to say is more of the technological age, and it's becoming of more concern just as our technologies become more sophisticated and more dependent on space weather impacts. So space weather does affect a wide range of critical infrastructure and technology, and because of its high latitude location, Canada is particularly vulnerable to these effects, and of course the socioeconomic impacts associated with them as well. Space weather, we can start with a definition. We like to say that it's a collection of physical processes beginning on the sun that ultimately affects human activities on Earth and in space. The sun is constantly emitting energy, and this comes out as flares of electromagnetic radiation, as energetic electrically charged particles that are regularly streaming out from the sun and are sometimes thrown out in spectacular explosions. And these particles will actually pull along a part of the solar magnetic field. So this is called the solar wind, and it's pulling along that interplanetary magnetic field that's coming from the sun. And this radiation and these particles in the solar magnetic field are going to interact with the Earth's geomagnetic field and outer atmosphere in complex ways that cause currents to form and cause fluctuations in our magnetic field. And this will cause geomagnetic storms and then disturbances in the upper layer of the atmosphere called the ionosphere. And these disturbances, they create the aurora, which of course is very nice, but they can also pose a hazard for human activities. There are three kinds of solar phenomenon that have major impacts on the Earth by disturbing our space environment. These are solar flares on the top here, coronal holes, and coronal mass ejections. So a solar flare is an intense burst of electromagnetic radiation across the electromagnetic spectrum, most notably invisible light and X-rays. And so this is a bright flash on the surface of the sun, and it can last anywhere from a few minutes to a few hours. Solar flares increase the amount of solar radiation that reaches the Earth on the sunlit side of the Earth, of course. So coronal hole, which you see in the middle plot there, is a region of the solar corona where the magnetic field lines are open to space, and this allows high-speed streams of plasma to stream out from the sun. And these high-speed streams, if they're larger or faster, I should say, than the background solar wind, are going to cause geomagnetic perturbations once they collide with the Earth's magnetic field. And this can cause storms on the Earth. It can cause particles to precipitate from the solar wind into the high latitude ionosphere, and it can cause these currents to flow and geomagnetic storms and ionospheric disturbances again. And then finally, we have a coronal mass ejection, and this is a big explosion that hurls particles into space. When I say big, I mean tens of billions of tons of matter. So we're talking on the order of about 1/8 the size of the moon for some of the bigger explosions. And the particles that come from this will actually reach the Earth in two parts. The first part is a burst of solar energetic protons that affect the ionosphere on the day side, high latitude region, so Canadian latitudes. And then a couple of days later, maybe as fast as 12 hours, as slow as 5 to 6 days, we'll see the arrival of the bulk of the plasma, which is a packet of energetic electrons. And this pulls apart of the solar magnetic field as well. And this will interact with our geomagnetic field and cause particle precipitation on the night side of the Earth this time. And this is where we'll see enhancements of the aurora. So here we see a coronal mass ejection exploding off from the sun. This particular explosion is going north or upward from the sun, so we can see it very nicely. So it's not really Earth directed in this case, but you can see that burst of particle or burst of plasma coming out. Activity on the sun, of course, won't influence us until it reaches us. So we're waiting for that solar radiation or those solar energetic particles and that magnetic field to actually reach the Earth. And they're going to interact with the Earth's geomagnetic field. So you can think of our geomagnetic field as a force field that's protecting the Earth from solar and interstellar particles. And without this protective bubble, our atmosphere would be stripped away and life really wouldn't be possible on Earth. So here you can see a visualization of our magnetic field, and we're looking at these blue lines of force that move out from one hemisphere and into the other hemisphere at the north and south poles. Solar particles and the solar magnetic field that are coming out from the sun will interact with our geomagnetic field. They're not able to directly pierce it. So they compress it on the front and they drag it out on the end to give it this kind of oblong shape that we see here. So that the sun would be on the leftmost side of the plot, and that would be the sun side of the Earth. And then we have our night side of the Earth. Whenever we have enhancements in the particle streams that are coming towards the Earth from the sun, that'll cause even more compression on the front side and even more elongation on the night side of the Earth in our magnetosphere. So there is some interaction between the solar wind and the solar magnetic field with the geomagnetic field. And this interaction will cause solar wind particles to become trapped in our geomagnetic field. And they'll actually funnel down into the high latitude region of the Earth, near the Earth's poles, in a region we call the auroral oval. And once they reach our ionosphere, they'll collide with neutral particles. And the result is this release of photons that causes light, which we call the aurora, in both the northern and the southern hemispheres. And the color of the aurora is going to be dependent on the types of particles that are involved in those collisions. We like to think of the aurora as the visual manifestation of space weather, because whenever we see the aurora in a place that we don't normally expect to see it, like Ottawa, that means there's some kind of space weather event going on. So the aurora, like I said, are regularly occurring in a band called the auroral oval. And in the northern hemisphere, that oval spreads across almost all of Canada. And this really makes Canada a unique country. So whenever the sun is very active, we'll see this auroral oval expand down to more southern latitudes, covering even more of the country. So like I said, seeing the aurora in places where you don't normally expect to see it means you've got some kind of space weather event. And it can actually become very dangerous for systems that are sensitive to space weather effects and sensitive to currents flowing in the auroral oval, because we might have systems at lower latitudes that are not used to the currents that are flowing in the auroral oval suddenly being affected by them when we have a strong space weather event. Here we go. Moving on to the technologies that are impacted by space weather. Each of the different solar phenomenon can have different effects and affect different technologies. So the charged particles coming from the sun are going to have different impacts than the radiation coming from the sun and the changing magnetic field coming from the sun. But they're all going to have damaging effects on the different technologies that they are that are sensitive to them. Geomagnetic storms are disturbances in the Earth's magnetic field. Like I said before, these can drive electric currents called geomagnetically induced currents, or GICs, in any kind of long conductor on the Earth. So this would be pipelines, railway lines, submarine cables, and of course power systems. And historically, the telegraph system was actually the first infrastructure that we saw impacted by space weather. GICs in power systems can cause voltage fluctuations in the lines, and that can actually trip out part of the system or even cause physical damage in equipment like transformers. In severe cases, we might see a blackout. And one really well-known example of this would be the March 1989 blackout of the Hydro-Quebec power system, which left 6 million people without power for 9 hours. I hope this is an audience that might have a few members that remembers this. I often talk to universities, and these kids I'm talking to have no idea what I'm talking about. Radio communication can also be affected by space weather disturbances that cause the ionosphere to absorb radio waves instead of reflecting it down to a transmitter. So radio communication over long distances works using high frequency signals in the 3 to 30 megahertz range by bouncing those signals between the ground and the ionosphere. But if the ionosphere becomes too disturbed, it can absorb that signal instead. Now, I was put onto a project studying high frequency radio wave propagation several years ago when I was on maternity leave. And I got really upset because I thought, who uses this kind of technology? It's obsolete. But that's absolutely not true. And it's actually in the forefront of our research right now because it's used by the aviation industry, it's used by the Coast Guard, it's used by the military, and a lot of different emergency response groups, either as a primary means of communication in some regions or as a secondary means of communication. Let's see what else. The ionospheric disturbances that are going to impact our communication systems can also have impacts on the signals that are traveling from the ground to satellites in space. So for example, that can interfere with GNSS signals traveling between transmitters on the ground and the satellites up in space. And that will reduce accuracy of positioning, navigation, and timing services. Any kind of magnetic disturbance can also interfere with anything that relies on a compass. So directional drilling, a lot of precision mining relies on compasses to steer the equipment, just to name a couple more examples. But today I want to talk about the space weather impacts on satellites. So satellites are located directly in between the sun and the Earth, so they're very vulnerable to space weather disturbances. Energetic electrons and protons can travel so fast, and there can be so many of them during a space weather event that they can actually go through the skin of a spacecraft into the electronic circuits, creating false commands, or damaging the circuitry, or causing a buildup of charge that could result in damaging electrostatic discharge. And satellites are very sensitive and very expensive instruments, but they have to be very light. So there's often not a lot of work put into protecting or putting protective materials onto the satellites. Instead, they rely on some really accurate modeling to try and determine orbits that are going to reduce space weather impacts. And just a small one electron can completely destroy a satellite. If our satellite is told, for example, to close its solar panels because of one of these false commands, or to turn away from the Earth so it can no longer receive signals, we could potentially lose our satellite. So these are very, very dramatic impacts. So just as an example, in 1994, we saw a failure of 2 INIC satellites. And this was a major source of impact, with some television services being lost to parts of the country and a loss of the pager service. And in 1994, this was roughly equivalent to the Rogers outage that happened in July of this year that forced about a quarter of the country off internet and wireless services. Now, there's one more effect that I want to talk about in a little bit more detail, and that's satellite drag. I am going to say right off the bat that I am not an expert in satellite drag, but this is something that's really interesting to me because of recent events, and I'll talk a little bit more about that over the next couple of slides. So any object that's moving through a medium, be it a liquid or a gas, is going to experience a resistive force. So this would be true for satellites orbiting around the Earth, and we would call this atmospheric drag or satellite drag for these satellites. So the magnitude of that drag force is related to the relative speed between the object that's moving and the object that it's moving through. So think about walking through a stream as an example. The force that you feel opposing your forward motion is drag. It's harder to walk against the current because the relative speed between the direction that you're moving and the current is larger than walking with the current, where the relative difference between your speeds is much smaller. And the magnitude of the drag force is also going to be dependent on the density of the medium that you're walking through. So this would be why, for example, it would be easier to walk through water than it would be through a thicker liquid like oil or pancake batter. So in the thermosphere, density is a function of temperature. So satellite drag is going to increase whenever we have atmospheric heating that causes the density of the atmosphere to increase. Now, this will occur predictably as the satellite orbits the Earth, moving through the sunlit or warmer part of the atmosphere and then the night side or cooler part of the atmosphere. But of course, we can have enhancements during space weather events that cause geomagnetic disturbances that we call geomagnetic storms. So here's the equation. I promise it's the only equation in my whole talk. It's not too bad. This is the equation for drag force for satellites that are orbiting the Earth. So rho here, or the P, is the atmospheric density. V is the relative speed of our satellite. So this is speed of the satellite relative to the atmosphere. A is the cross-sectional area of our satellite. So here, our little satellite here has a round dish, and then the solar panel. So we've got our cross-sectional area here, and that gives us our drag force. And the only other thing we have is a drag coefficient here. This is a pretty straightforward equation. It's not too bad, and we can use that to calculate our drag force and compare that to the different forces that are acting on the satellites to learn exactly what this drag does to the satellites. So if we were to look at the balance of forces on that satellite, and we were to look at the conservation of energy, balancing between kinetic and potential energies, we would find that as our satellite moves through space experiencing drag, we'd see that as drag increases, the satellite will start to drop in altitude. Now, we call this orbital decay, and this is normal, but satellite drag speeds up the process and reduces the lifespan of the satellite. So if the orbital decay is too significant, or if the satellite's already at a very low orbit, it can drop and burn up in the Earth's atmosphere. And although this is great for removing small bits of space debris, it can be very expensive and even devastating when we're talking about satellites. So satellites can correct their orbits when needed, but unexpected drag due to space weather events can cause them to use up fuel and reduce the satellite's lifespan. So when the sun's quiet, satellites in low Earth orbits have to boost their orbits about 4 times a year to make up for atmospheric drag. But when the sun's active, these corrections have to be made every 2 to 3 weeks. So this needs to be taken into account when you're launching a satellite. Now, there are sophisticated satellite drag models, and these are used to predict the future locations of satellites and space debris when satellite drag predictably or even sometimes unpredictably alters their course. And there are space weather forecast models that can be used to inform these satellite drag models to protect, just as an example, astronauts on the International Space Station. So the space station can use collision avoidance maneuvers if the probability of collision starts to become too high. And during its first 15 years of operation, sorry, I couldn't find statistics after that, there were 16 collision avoidance maneuvers successfully conducted by the space station, just to give you an idea of how frequently these happen. Usually these maneuvers would consist of increasing the orbital velocity of the space station on the order of about 1 meter per second, and that would boost its orbit by about 1 to 2 kilometers per second to move it out of the way. If there's not enough time to perform a collision avoidance maneuver, the crew of the space station would actually have to retreat to their spacecraft, where they would be prepared to undock from the space station quickly in the event of a collision. So I've got a little video here that I want to show you, and we'll see if we can get it going. Oops. YouTube. No, hopefully I can get it to play. I'll give it a second to get started here. So the consequence of satellite drag can be enormous. And we learned this actually earlier this year. Sorry, my YouTube clip was working earlier, but it's going to be a little stubborn now. Okay, I'm going to let it spin, and if it starts to play, that's fine. On February 3rd at about 1:13 Eastern Time, 49 Starlink satellites were launched into a low Earth orbit from the Kennedy Space Center in Florida to an orbit of about 210 to 240 kilometers. The satellites were first put into these low orbits to, oh, here we go. There we go. Okay, it'll buffer and I'll stop. The satellites were first put into these low orbits to allow any faulty or problematic satellites to be deorbited safely. This is a really good strategy for reducing the accumulation of space debris, which is a major concern for long-term sustainability of space activities. Once the satellites are evaluated, they're raised to a safer operational orbit of about 500 kilometers. The day after the Starlink satellite launch, very minor geomagnetic activity caused an unexpected 50% increase in atmospheric density on the dayside low latitude region of the Earth. And this dramatically increased drag on the satellites, especially at these low altitudes where the particle density is much higher. And this rapidly gave the orbits. Starlink reacted to the space weather event by turning the satellites into a safe mode, allowing them to fly edge on instead of face on into their orbits to try and minimize drag by reducing that cross-sectional area of the satellite. But this drag, it proved to be too much, and this prevented some of the satellites, actually most of them, from rising to a higher and safer orbit, and instead caused them to drop out and re-enter the Earth's atmosphere where they disintegrated. 38 of the original 49 satellites were lost, which is what you're watching right now, at a cost of $50 million US. This is a really powerful example of space weather that demonstrates the significant practical and financial consequences of it. And what's really interesting about this event is that it even happened in the first place. The solar activity associated with the event was really minor. There was a moderate level coronal mass ejection, a moderate level solar flare several days before the launch of the satellites. The CME that produced this explosion wasn't moving very quickly. We didn't really expect a lot of activity. On February 3rd and on February 4th, we saw some small bursts of activity in the solar wind, which were associated with little bursts of geomagnetic activity, but the activity wasn't large. You know, we saw some northern lights at lower latitudes where we wouldn't normally see them, but there was nothing really exceptional about the event, and none of the international space weather centers put out any kind of strong warnings. When there is a geomagnetic storm, we would typically expect higher latitude ionospheric heating than what we saw here. So than where these satellites were located. So we did see some high latitude heating on the night side of the ionosphere, but the satellites were located really close to the equator. And for this particular event, there was also heating on the sunlit side of the ionosphere at equatorial latitudes where the Starlink satellites were orbiting. So the peak dayside electron density did increase by about 50%, which is what the satellites observed, causing the satellite drag that ultimately destroyed them. So this new phenomenon is something that will have to be incorporated into future satellite drag models. And that's actually all I wanted to say today. I just wanted to leave you with this slide. I think it was NASA who put it out, just showing the difference between the sun during solar minimum and solar maximum. So the sun moves through a period of solar activity. It's an 11-year cycle. When the sun is very quiet, we don't see a lot of activity, but when it's very active at the high part of the cycle, we see a lot of coronal mass ejections, a lot of sunspots, a lot of solar flares, and we're actually expecting our maximum of this cycle in 2025. And this is proving to be a very interesting solar cycle so far from a space weather perspective. Thank you so much for listening. I would be more than happy to answer some questions.
Yeah, we have a couple of questions here for you, Robyn. Thank you. From Michael Wolfson, apparently in geologic time, the north and south poles of the Earth's magnetic field have reversed. If this reversal isn't that quick, could the sun's CME strip away some of the Earth's atmosphere?
Yeah, and this is actually a really common question that we get. So yes, the magnetic field does reverse. I think it reverses on the order of every about 300,000 years, and we haven't seen a reversal for about 750,000 years now. So a lot of people start to think that we're due for one. When the poles do reverse, historically, we notice a reduction in the overall magnetic field. We sometimes see some changes in where the magnetic poles are. Sometimes we would actually see more poles as well, but we've never seen the Earth's magnetic field disappear. So there's no reason to think that that's something that would happen in the future. The other thing to remember is that the magnetic field of the Earth is a function of the solar magnetic field coming through the Earth, or coming across the Earth, and motion of the plasma inside the Earth as well. So we've always got this generator inside the Earth. So the solar wind can't strip away our magnetic field. It actually fuels it and helps it be possible. It seeds our magnetic field.
Okay, thank you. And Danny has a question. Fascinating talk. Could some of the disturbances you described be hard to track and be dangerous to astronauts? There's not enough time to complete an escape maneuver.
Yeah, and that is something that's of interest, especially when we have solar flare events that are introducing radiation to the Earth. So these coronal mass ejections, we typically have lead time for them. There are satellites that are located between the sun and the Earth that can give us as little as 30 minutes lead time to see some of that activity. But with increased activity by astronauts, so when we're looking at missions to the moon, for example, and missions to Mars, this is something we really have to be aware of, because our astronauts are no longer going to be within that protective bubble of our magnetosphere. So there has to be some kind of consideration into shielding that can be placed onto the vehicles that the astronauts would be in, or the space stations that they would be on, so that they can go to safe and protected regions with as much lead time as they have. And I mean, when we have an explosion on the sun, we don't know that it's happened until it's arrived when we're talking about these solar flares. I mean, it's 8 minutes for that radiation to reach the Earth. So that's not something we can really predict. But these coronal mass ejections with the more damaging energetic electrons and energetic protons, that's something that we do have some notice of, fortunately. And there are a lot of models that are going about to try and improve probability models to predict when we're going to have a solar flare. And once we have stronger and better models and more confidence in them, that'll be something that we can act on. Because you can always get into this situation where you're predicting a solar flare, but too many false alarms will make people complacent to them, right? And that's kind of the spot we're in right now.
Absolutely, yeah. Ken has a question. Is there any significant source of space weather other than the sun?
Space weather at the moment largely encompasses the sun. But when we're talking about space weather observations that we make, one of the instruments that we use to evaluate ionospheric disturbances is called a rheometer. And actually, I was really happy to hear you mention Marcus Leach at the beginning, because this is something that his group develops as well, and he's done some work with our group with rheometry. So what they're doing is they're measuring how opaque the ionosphere is by looking at the amount of intergalactic cosmic noise that's coming in. So if the ionosphere is more disturbed, we're going to see less noise than when it is less disturbed. So we can look at the level of noise that we're seeing and compare that to what we would expect to see on a quiet day to try and determine how disturbed the ionosphere is. So there are different sources that we're looking at to try and get this information to characterize what we call space weather.
Okay, well, thank you very much, Robyn. I don't see any more questions in the queue here.
Actually, yes, we do have another question that was put
in
into
the chat okay.
room. So, Robyn, from Robert Dick, the growing low Earth orbit satellite constellations are well within the Van Allen belt. Is their performance and reliability still sensitive to space weather? And his question is focused on the exposure to radiation.
Yeah, and actually something that our group has been involved in before is modeling satellite orbits to try and calculate the different kind of exposure that they're going to be under. So definitely that's something that's taken into consideration. I can't really give you anything more exact than that because it's not something that I'm actively studying, but certainly we do look at particle models, and there have been satellite missions specifically focused on the Van Allen belts and trying to characterize the particle distributions.
Great, thank you. And there were also two other reactions to your talk in the chat room that were fun. One, you brought back memories for one person of being in a pub in Quebec then at the moment of the major power failure. He remembers it well.
It is nice to have someone not give me a blank expression when I mention it.
There are many in this group who will remember it well.
Thank you.
Saying nothing about our ages.
And we got some cheers as well when we saw the image of the burning up of the Starlink satellites.
Yeah, that was really interesting. I was wondering if maybe you'd had any kind of presentations on that after it had occurred.
Well, we certainly know the issues they have in blocking our view of the deep space. So,
oh,
that's what the cheering was about.
Well,
yeah.
Thank you again, Robyn. I really appreciate the fascinating talk. I know many of the members have commented how much they enjoyed it. So thank you so much for being able to join us.
Well, I appreciate the invitation. Thank you.
Great. Okay, at this point, we would normally move to our next talk, which was to be given by Mick. Obviously, he won't do that, and I'm not going to try to do his talk for him. So we'll move a little early into the break. And following tradition, Mick has posted a interesting question here for you to ponder over the break. So we'll stop for 5 minutes for what he would call a bio break, and we'll see at the end of the 5 minutes if anyone has figured out the answer to this. So see you back shortly.
So
Okay, we'll move on then to the answer to this. And following the chat room, congratulations to Larry Penn, who sensed that this may not be an astronomy question. A creatively worded question by Mick, and the answer is the world's first traffic light became operational. Okay, we move on to our second major speaker tonight, and we welcome back a most regular speaker and such dedicated astronomer as we have fortunate to have in our group, Rick Wagner. Among many of his passions, he's an outstanding astro-imager and has really been very successful at working with the RASC various observing certificates, both visual observing and imaging. And he's going to give his second talk on the next of the Astro-Imaging certificates. So welcome, Rick.
Thanks, Chris. Good evening, everybody. It's really good to be here again. Just wanted to remark on what a great few weeks we've just come out of. Tonight is going to be my 12th clear night of observing out of the past 16 nights. And that doesn't include an additional 4 nights of clear weather with the RASC remote telescope in California. So 16 out of 16 is not a bad record. Anyway, last month, I talked about the wide field Astro-Imaging certificate. And so I thought tonight I will continue on with the next in the series, which is the solar system certificate. Next slide, please.
And my apologies, Rick, in the early introduction, I mistakenly said it was deep sky, but of course it was wide field.
Yeah. So to recap the program so far, there are 3 different certificates: the wide field, solar system, and deep sky. And all these certificates are available to RASC members only. So there's something to, an additional encouragement to join the society. If you go to rasc.ca/Astro-Imaging certificate, you can see the details on what's required for each certificate, download the application forms, and see a list of those who have already received their certificates. And rascastroimaging.zenfolio.com has the image collections submitted by all the past recipients. Well worth a look. Next, please. So the solar system certificate is obviously focused on imaging targets in the solar system. However, it's actually even more narrow than that. Comets and minor planets are not included. And this is really rather appropriate, as comets and minor planets really require techniques that are a lot more akin to deep sky imaging than planetary imaging. So this certificate is the most prescriptive of the 3. And I guess you sort of have to expect that, given that there's only the sun, the moon, and 7 major planets, not including the one we live on. And so in addition to that, the certificate doesn't even make mention of Mercury, Uranus, or Neptune, all of which show little to no detail in Earth-based telescopes, so aren't really worth imaging very much. There are 8 images required, some duplication of targets, but some variety in techniques. Next, please. So the goals are to develop the skills of focusing, tracking, stacking, and image processing. Now, you might look at these and think, oh, that sounds like all the basic skills that are required for any astro imaging. But given that the targets are generally small and bright and are often imaged with very long focal lengths, often using video technology, the techniques are quite distinct from deep sky or wide field imaging. Next, please. So the requirements, as I said, 8 images of specific targets. For each image, you have to document your equipment and settings, the location, date and time, processing that you used. I like to include any planning you did, problems you encountered, or interesting circumstances to add some interest, background interest to the images. Next, please. So here are the 8 requirements and the images I submitted. The first is a snapshot of the full moon. Now, by snapshot, they mean a single frame. This one I took with an old DSLR, my Canon 60DA having died, so I went back to my Canon 30D on a 10-inch Schmid-Newtonian. This was an unexpectedly challenging image because I only suddenly noticed the rising full moon early on an evening that was forecast to be cloudy. I rushed out to the telescope, but the moon was too bright for the CCD camera on the telescope, so I had to switch to the DSLR. Then focusing was very difficult because this camera doesn't have live view, so I had to try several different techniques to achieve good focus. And the forecast cloud was moving in rapidly from the west. So this was the only successful image that I took, just seconds before the moon disappeared for the rest of the night into the deck of cloud. Next, please. Next, yeah, there we go. Okay, the second requirement, a snapshot of the moon showing crater detail. This image is a single frame that I took with an ASI 174 mono camera on the Boltwood 16-inch scope. On the terminator at the bottom, you can see the lunar X, and it's right next to the shadowed crater Werner. And just peeking in at the top left is the bottom of the lunar V, which appears at the same time, roughly, as the lunar X. The two biggest craters in the Albategnius. Next, please. The third requirement is a shot of crater detail using stacking, which is usually done from captured video. So this image is actually a mosaic of 2 frames. I used the fire capture software to capture videos with the ASI 174 camera on the Boltwood 16-inch scope with a 2x Barlow. The sharpest 10% of several thousand frames from each of the 2 videos were stacked in software AutoStacker 3 and then combined in Photoshop to produce the mosaic. Just to the upper right of center, you can see Rima Hyginus with the crater Hyginus in the middle of it, and beyond it, further to the right, Rima Ariadeus. Slightly to the lower right of center is the very nice round crater Triesnecker and its eponymous Rimae. Almost dead center is the small crater Eucert, surrounded by a raised terrain, which are cut by deep gouges running from the upper left to the lower right. These gouges are actually huge gullies that were cut through the terrain by mountain-sized boulders flying out from the Mare Imbrium impact. I would hate to have been there as those mountains slashed their way through the surrounding terrain. Next, please. Fourth requirement is a picture of Venus. Now, this is a picture of Venus. Something I had wanted to do was get a picture of Venus at the moment of inferior conjunction, when it's at the same right ascension as the sun. However, we had several days of cloudy weather forecasts, so I knew I wasn't going to get it. So this is 3 days before inferior conjunction, taken with a DSLR in movie mode. I was using a Takahashi Sky 90 refractor with an extender Q, which pumps it up to f9. And although I like this picture, the live event I watched through the Boltwood 16-inch, which showed Venus as an unbelievably thin crescent dancing in the midday turbulence, like a beautiful white eyelash in the sky. And let me tell you, it can be a bit intimidating aiming a 16-inch telescope within a few degrees of the sun. Not something you want to do without a great deal of care. Next, please. So the fifth requirement is an image of Jupiter or Saturn showing the moons with labels. And this one, for me, it was actually prompted by a mistake. I was trying to shoot for the planet, but my first video, I neglected to reset the exposure times and ended up picking up the moons. So I adjusted and repeated that several times to improve things, and eventually came out with an image showing the 4 moons reasonably distinctly. I think in hindsight, this would have been much easier to do using a still camera, and I may try that again sometime, especially now that Saturn's coming towards opposition. Next, please. So the next 2 requirements are planetary shots of 2 out of Mars, Jupiter, or Saturn, which are the only 3 planets which show an obvious disk and appreciable surface detail in our telescopes. So this is my best image of Mars from the last opposition 2 years ago. taken with a QHY 178 color camera through a pair of stacked 1.8 and 2 power Barlows on the Boltwood 16-inch for a total focal length of 7 meters. It's a stack of the best 10% of frames from a video captured with fire capture. Next, please. Oh, the video even shows up. So this is a series of videos I shot of Jupiter, again with the Boltwood 16, with the QHY 178 camera, but just the 2 power Barlow. Jupiter gets absolutely enormous at a 7 meter focal length. So the same processing, except that I had maybe a dozen videos, and I processed each of them and then linked them all together into an animated GIF. This was at last year's opposition, so I'm really looking forward to trying again this year with Jupiter 20 or something degrees higher in the sky and maxing out at a width of just a hair under 50 arc seconds. Unfortunately, I don't yet have a nice image of Saturn. Next, please. The final requirement is an image of the sun, either in white light showing sunspots or in H alpha. And this is a good time to be doing that as we're moving in towards solar maximum. This particular picture is a combination of 2 H alpha images of the sun, one shot to expose the filaments, faculae, and granulation on the disk, and a longer exposure to bring out the prominences. And then the 2 images were blended together in Photoshop. And that's the 8 requirements. So next, please. As with all the certificates, you take your pictures, scale them all to 1200 pixels long or smaller. Some of the planetary images aren't going to look very good 1200 pixels wide. Name the files so that it's easy to match the images against the requirements. Add the completed application form and image documentation, and then email the whole bundle to the Astro-Imaging committee. And you should hear back in a few days, hopefully with agreement and notice that you've been awarded the certificate. So next, any questions?
I'll start with a question for you, Rick.
Okay.
While there's many in the audience who will know exactly what you mean by the Boltwood 16, there'll be others who won't know what it is. And if they go looking on the web to try to buy one, I don't think they'll find one. So maybe you can explain.
Yeah. Paul Boltwood was a very long time member of the Ottawa Centre, outstanding observer, and almost painfully detailed designer and builder of the telescope that I now have. So it's a 16-inch, roughly f5 Newtonian on a Mathis Instruments 750 mount. He designed and built it all, had it machined by a local guy in Ottawa. And when he developed an illness, perhaps 6 or 8 years ago, he decided the scope needed to be used by somebody. He could no longer use it. And he donated it and the mount and the camera to me. And I hope Paul would approve. I've probably shot probably 200,000 images with it in the years since he gave it to me. So
I've had the pleasure of seeing it in his observatory with him, but it's fantastic to see that it's in its second life and still able to be used and appreciated. And so thanks, Rick, not just for the excellent talk, but of course the reaction that we would most like to hear to your talk is from someone in the audience saying, I think I could do that. Maybe I should go out and try a certificate. So it really doesn't matter which certificate you start with. Sometimes the discipline of having a certificate like this is what motivates or forces you to go through it in a detailed way. And encourage you on in the field.
It certainly encourages one to cover the range from solar to lunar to planetary. So rather than just picking on a specific subject and out of the gate.
So we have a question, Rick, from Richard Taylor. For solar images, would a photo of a projection on a screen be good enough?
I don't know. I guess you'd have to take it and submit it, see what they say. I know some of my acquaintances have had a little trouble with getting their images successfully admitted, but yeah, I think they would try and encourage the observing more so than insisting on particular types of equipment.
I'm assuming, Rick, going back to your last slide, someone could send an email to that RASC Imaging at rasc.ca and pose the question in advance.
Yes, probably.
So thank you again, Rick. We'll move then on to, and we'll look forward to your next installment whenever you're ready.
Right.
Moving on to our observation reports, and again to the observers, take a look at the chat room to see the order that you're speaking in. But we'll start with Tony Peterson, who's...
I'm here, Chris. Can you hear me?
Absolutely can hear you, and just wanted to
Excellent.
comment that Tony's taken a very creative approach to how to present an observation. So,
this was actually meant just to be YouTube, and I thought, well, okay, I'll give it to RASC, and well, you accepted it, so it's your fault.
Okay.
Yeah, it is. Okay.
Tell me when you want me to start it.
Well, you can start it, and then as soon as the first screen comes up, just pause it. You can pause it. Okay, so I finally broke down and got a solar scope this winter, and I've reached the point where I dare to try time exposures. You're going to see the first result today. It's full of a lot of, I would do things differently, and I promise it'll be better next time. So like I said, there is a 4K version of this entire video up on YouTube. So I set it up. I don't need to talk very much. Go ahead, Chris.
Hold on. I forgot to enable sound. I'm just enabling that.
Yeah, it doesn't come on for a little while. Well, not true. I heard that. Pause there, Chris. I just want to make a small correction. That filament is not in the chromosphere. It's actually floating up in the lower corona. Okay, go ahead. And one more pause, Chris. So, that's okay. Go ahead. That's okay. Okay, so these video bits were collected at different frame rates. I've tried to run everything at 10 times normal speed. I promise you, if you stare closely enough, you can see the flare moving. That's all. Go ahead. Oh.
I'm afraid I may have caused that to restart. Sorry for this technical issue, and I'm not sure what's caused this to go wrong. So I'm actually going to go back and restart without pausing. No.
There's the real stuff. These are only single stacked images, just a pressure tuner. I'm not using the double stack with these yet.
So we'll just let this play without pausing it so I don't
Sure. Yep.
cause the problem again.
We'll put our hands in our pockets. I tried to look for that filament as it came around the other side. I had a photograph of an appropriate date. It was gone, as far as I could tell. Once more sneezing. That's so no one has to ask me any questions. Okay, there's your warm-up act.
Fantastic. And Rick Wagner thinks you've already submitted your solar image for your certificate.
Yeah, right. Okay.
Thank you. We'll move on to our next observer with Andrea.
Well, obviously the sun is a big hot topic these days, and these are just some of the images that I also took end of June into July. And there's been obviously so much activity going on. It's really fun to watch. These were all taken, exactly, hot topic. These were taken with my 40mm lens, and I've been trying to take a full disc image every day that it's sunny. And you can really see how things are really changing. And if this isn't at the full peak yet, I can't even imagine what it's going to be like when we get there. 3 of these images are inverted. So a black sunspot will appear white, and the one in the upper corner is not inverted. The picture of July 15th, you'll see there's a big white flare. It was actually a massive, humongous filament that I could see in black when I looked through the eyepiece. And it was there, and then it totally disappeared and shot off into space. And next image. I put these together. This is sunspot. They're all given designations. 3055, I believe, was this one. And the image is taken in black and white. And black and white is nice because it gives a lot of contrast. And the white area is a solar flare area. The black part is the sunspot. Then what happens after we take an image in black and white, we do a false color image. And then often we invert the image to see it in a whole different light. So this was one of the more spectacular sunspots that crossed the sun's face on July 15th. Next. These are two, this is an image taken up at the beginning of the month and closer to mid-month. It's following the same sunspot, 3053. From when it began, it came around the corner of the sun, and then it traveled all the way across, and it was a highly active area, and lots of people were photographing it and watching it go across the sun. And it, at the very end of its journey, there was a great big giant filament, and I saw it on Tony's video as well. And you'll see in my next slide, I also did an attempt at an animation. And I didn't quite get my color as nice as Tony's color. So we'll just go to the next slide now. And you'll see in this video, actually at the very tail end of my time lapse, there was a solar flare eruption. And if you keep your eye on this, on that white spot, you'll see it. It's going really slow. In any event, oh, there it is at the very end. So I sort of stopped my animation a little too soon, but I think what's fascinating is that the sun really is in motion nonstop. There's always something exciting to see. And this was, of course, a massive solar prominence that was very, very visible and very dramatic on that day. And I'm just going to flip now to the next slide because, again, so people don't ask, and they often do ask, the equipment. This is the Lunt 40 millimeter. So it's smaller than Tony's instrument. It's not pressure tuned, but it's tiny and it's very light. And I use it on a Star Adventurer. So this is generally, it's a rather economical way to look at the sun. And the Star Adventurer has a solar tracking speed. And you can use a Barlow if you want to increase magnification. I would use a Barlow for some of the close-ups of the prominences. And if you are interested in this, the Astronomical League on their website has a solar observing program, and it gives a lot of information. And I've been looking at it and working through their program, and it might be a fun place for people to start as well. So thank you.
Thank you, Andrea. An incredible detail in those images. And I recall you only recently started solar observing. So it's amazing.
I just started in May, and I'm getting so much sleep. It's wonderful.
Okay, our next presenter, according to Dave, is Bob Marley. So, Bob, we expect another performance to suit.
Yeah, no solar stuff. July was a very productive imaging month as I got out 18 nights, no sleep, but lots of data. When you look at this image, you might think that I missed the target of M13. You would be incorrect, as the center of the image is NGC 6207, one of the July challenge objects. The other challenge objects were below my horizon. Next image. This galaxy is visible visually in a telescope and is aptly named the Splinter Galaxy. It is about 50 million light years away. Next image. This pretty open cluster was discovered in 1781 by one of Messier's collaborators, Pierre Machin. It's about 9,000 light years away. It features a very prominent red giant. I find this picture very attractive view in an eyepiece also. Next image. This close-up of the North American nebula is so zoomed in that the only recognizable part is the Gulf of Mexico. It was first noticed by William Herschel in 1786. It is near the star Deneb and is about 2,500 light years away. This really needs wide angle. My scope is not wide angle. Next image. This is the brand new image of the Stephan's Quintet that we saw actually last month by the James Webb Space Telescope. And this encouraged me to try the target myself. Okay, next image. Obviously, my scope doesn't have the reach nor the resolution of the James Webb Space Telescope, but there is detail. 4 of these galaxies are in a compact galaxy group. The slightly whiter galaxy to the left is about 30 million light years away. The rest are about 300 million light years away. The 2 very close together at the center are colliding at several million kilometers per hour. They are responsible for the shock wave that is producing the long streamers of stars being ejected from the galaxies. Next image. Yeah, this is what the James Webb Space Telescope image superimposed on mine would look. This is what they're the same scale now. Next image. The Lagoon Nebula. It's a large star-producing cloud in Sagittarius. It's easily visible in almost any telescope and is a must-see summer object. It's about 4,100 light years away. Get out this summer and take a look at the Sagittarius. There's 100 things in there to look at. Right south near the horizon. Next image, please. The Irish Nebula, I'll spit it out yet. The Iris Nebula is a reflection nebula about 1,300 light years away. The blue is the result of differential or preferential reflection of blue light by dust. Blue light reflects off dust better than any other color. This is also why our sky is blue. Thank you very much.
Thank you, Bob. And next we move to Oscar.
Hey everyone. So I missed last month. I was on a drive home from Toronto, and then when I got back, I completely forgot that we had the meeting. So I know this meeting was included in last month's slide deck, but I'll speak to it today. This is an image of the spiral galaxy named the Lost Galaxy of Copeland. That's the spiral galaxy at the top left there. It's cataloged as NGC 4535, and it's a barred spiral galaxy about 54 million light years away in the constellation Virgo. It was first observed in 1785 by William Herschel, but its hazy, ghostly appearance through smaller telescopes gave it the moniker the Lost Galaxy when amateur Leland Copeland dubbed it such in the 1950s. In the bottom right, the larger galaxy there in the bottom right is a lenticular galaxy, NGC 4526, also classified as a spiral. And if you were to zoom in into the core, you can kind of see some spiral structure. It's 55 million light years away. It's one of the brightest known lenticular galaxies. Sorry, lost my train of thought here. An interesting note about the galaxy is the orbital velocity of its globular clusters, whose low speed indicate that there's an abnormal absence of dark matter in this particular galaxy. This image was taken on the night of May 29th with the ZWO ASI 2400 MC Pro through an 11-inch Edge HD at f7. It's 7 600-second sub-exposures, so about an hour and 10 minutes of exposure for this one. All right, next image, please. All right, so this is the Hercules cluster of galaxies, also cataloged as Abel 2151. It's a cluster of galaxies, some 200 galaxies, about 500 million light years away, and it has many interacting galaxies. Could you click it once there, Chris? I'm just going to zoom in here. If you could just advance it. Yeah, there we go. Yeah, so there's many interacting pairs, as you can kind of see all around there. One more time there, Chris.
I think it went 2 shots in 1 click. There was the intermediate.
Okay, not quite the position that I had it in, but that's all right. I'll speak to it regardless. So if you look kind of near the top, am I able to point on this somehow?
Only if you can call up the, no, in fact, you can't.
Okay.
Yes, you can if you use the annotate feature.
Uh-oh, what did I do here? Anyway, I'll just try to describe it as best I can. Kind of near the top, just right of center, you can see kind of 3 galaxies that are interacting. That's ARP 272. That's it there. And that was the focus of my observation here. So it is the 2 larger galaxies are a pair of interacting spiral galaxies, which are NGC 6050 and IC 1179. And these guys are about 450 million light years away, and they're interconnected via their spiral arms. And in between is another third galaxy there, who's kind of caught in the crossfire, also interacting with the other 2. So this image was composed of 6 hours of exposure at with 10-minute subs using the same ASI 2400 MC Pro camera, same telescope, the Celestron Edge HD 11-inch. And it was taken over the course of 3 nights, the 25th, 28th, and 29th of July. All right, I think that's it for me this month.
And there was the next zoom in.
Yeah, I think I set it up differently on mine.
Okay.
It must have not translated.
Okay, thank you, Oscar. And if you're able and wanting to present your challenges later, we'll get to them shortly. We'll move in the meantime to John Thompson.
So all the pictures that I was displaying here are wide field shots, sort of like the ones that Rick was describing for the certificate. I was a week before last, I was attending an astronomy camp in Upper New York State. It's mostly Americans, but there's a few people from Ontario there also. And this was really the first dark sky trial of a new lens I had acquired, an 8mm, which on a cropped frame camera, I've got a Canon, is not quite fisheye. It gives about 120 degrees across the horizontal and nearly 180 across the diagonal. But this is looking in the direction of northwest, and almost in the center is Denny, just a little above center. And then if you look above right and to the right of it, you can see the summer triangle there. But this is just like when you're actually out under a very dark sky like this, there's so many background stars that the constellations sort of disappear. The W Cassiopeia is down in the sort of lower left near where the Milky Way sort of disappears, but again, it's sort of hard to see. Next shot. Next. Now this is looking southwest, and off to the right is the cabins and the lodge where we had our meetings and the eating area, and people in the foreground with their equipment. But again, this is sort of the other part of the Milky Way. Again, Deneb is close to the top of the frame, and Altair is further down. Vega is off the top. You can't quite see it, so we see 2 stars of the summer triangle there. Right, almost center, a little above and left of center is a little constellation Delphinus, or the little dolphin. And then you can see as you get down to the lower part of the Milky Way, you're looking into the center core of it, where the brightest part, a lot of dust clouds, the biggest concentration of stars. Sagittarius, it can just be seen actually over the treetops there. Actually, part of it has disappeared, but the brightest part there is sometimes referred to as the steam of the tea kettle, because Sagittarius looks like a tea kettle or teapot. And Antares and Scorpius is just barely off to the right. Next 2 shots are what I call astro selfies, I suppose. I'm trying to take portraits of myself. This is sort of like in the 19th century when people had to sit for, perfectly still for a minute or more because of the slow speed of the films. Oh, in these cases, I was standing as still as I could for about 75 seconds in order to get these images. I had tried this about 15 years earlier, and with less satisfactory results. But this time, because the lights in the cabins and the external ambient light was less, my face came out a little better, because in the previous ones, it was glowing bright red, almost as if I was badly sunburned. You can see off to the left is the observatory at Celestron 14, which unfortunately wasn't working at the time. But again, you can see the Milky Way there, and then I believe there was an aircraft left that trail to the left. Okay, next one. This is just another perspective. There was a little patchy cloud running through there. It obscures a bit of the Milky Way. But again, just above center is Altair and Aquila. And you can see to its lower right is the Scutum star cloud. And then I'm down there looking sort of towards the meeting area. And there's another satellite or plane right at the very bottom. My last slide this is what really inspired me to try this sort of thing. This page appeared in, I think it was February of 1986 in a magazine called Science Digest. And I was always impressed, not just the poem by Ray Bradbury, but also that image. I was always wondering if it was possible to try and actually capture something like that. And I think I'm getting close now. But the poem itself, Ray Bradbury wasn't well known for his poetry, but he really nailed it. On this one, I think he's describing what Galileo, as a young child, maybe 10 or 12 years old, was thinking as he looked up at the sky. And it really resonated with me because I had sort of the same impression. My earliest impressions of looking at a dark sky were sitting on the sand in Lake Huron at my uncle's cottage, listening to the waves come in and just being overwhelmed by the majesty of all these stars and the Milky Way. I'm going to publish this in Astronauts, but I'll just end by quoting the last 4 lines, which I think were significant. The universe is thronged with fire and light, and we but smaller suns, which, skimmed and trapped and kept, enshrined in blood and precious bones, hold back the night. Thank you.
Thank you, John. Moving now to Tom Taylor, who we haven't seen for a while, presenting. Great to have you back.
Yeah, hi. These are a few images. I just recently got the narrowband filter, so I've been starting to use those on the scope. This is C27 Crescent Nebula, RGB with using the hydrogen alpha as a luminance layer. So this was captured over June 23rd to 25th, basically the images for this stack. And I'll probably capture some more light and keep building on this. I think it's only up to maybe 30 or 40 minutes per color right now. So next one. Now this is M16 Eagle Nebula. I've just started to capture this. So this is just the LRGB. I haven't captured really the narrow bands for this yet, which is quite bright. So I'm dealing with, what exposures to use and things like that. But the image seems to be coming up pretty good. You can see the, the pillars of creation there, the famous Hubble image. And, the eagle's head is starting to show up there in the top left, but it's coming along. But hopefully I'll be going out tonight to capture some more light for that. So we'll see. Next one. And I tried to capture some image of the C-2017 K2 comet there. So this was on July 14th, 15th, when it was passing very close to M10. And I hadn't used the Deep Sky Stacker Comet mode before, if you want to call it the Comet mode. So I had to learn how to use that. So I did stack actually both images with the stars fixed and the comet trail versus the comet fixed and the star trails. They both look good. I put this one up. You can see faintly the tail going off to the right there. And this is strictly a monochrome image on the luminance filter on a monochrome camera. And I wanted to see, of course, I can't capture too many more images of this. It's on its way out. But I want to keep working with this data a little bit to see if I can bring up the contrast of the comet tail and things like that. And the next one is the same comet on July 23rd. It's moved away from M10. Again, this is a monochrome luminance only image. And you can see the tail a little bit better in this one. I think the night was a little clearer and seeing was better. So yeah, it was good to be able to capture that comet because it's going to be gone soon enough, I guess. That's it. Thanks.
Great. Thank you, Tom. We'll look forward to seeing the same images with more exposures added later on.
Yeah, I'll keep working on M16. I've only got, well, I don't know, maybe a few more weeks left where it'll be visible from my location. It's pretty low in the sky for me right now. And as the summer wears on here, it will disappear. So I haven't been so lucky to have, 12 nights of clear skies over the last 16. I'm lucky to see if I get 2 or 3 or 4 a month, it seems, recently. So it's pretty shallow sometimes.
Great. Thanks again, Tom.
There was a question there that I stacked the comet and stars separately. No, that's it's using this standard deep sky stacker, but it has a mode in there where you, if your images are in time sequence, you can pick your reference frame. So you do the normal registering, and then you can designate your reference frame. And then you go into the first frame, the reference frame, and the last frame, and you designate the nucleus of the comet. And then Deep Sky Stacker interpolates through the time sequence of your images where the comet nucleus needs to be, and then it stacks them up to get this image. If you don't designate the nucleus of the comet and just do regular stacking, this is what you get. If you designate the comet nucleus, you'll see the star trails, and the comet nucleus will be the fixed point. So it's just done with a simple step in deep sky stacking.
Okay, thanks again, Tom.
Thanks.
And we'll move, as always, to our final presenter, Paul Cloninger.
Oh, thank you, Chris. Is my audio good?
Excellent.
Awesome. Okay. Well, good evening, everybody. And you know what? I'm really glad to hear I'm in good company with respect to sleepless nights under the many clear skies we've had in the last few weeks. That's a real bonus. I hope to go more sleepless even tonight. Anyway, my observation for this evening is a follow-on to last month's, where I continued my testing of the ASI 294 MC Pro color imager on some wide-angle views of the Milky Way. This month, most of my imaging has been with the camera on the 11-inch Edge HD at f10, but with a bit of a twist. I've been testing it using the ZWO dual band filter in addition to regular full spectrum RGB imaging. In that regard, my observation is also a follow-on to the presentation I gave last November on the nature of narrow band imaging. The dual band filter offers some interesting imaging opportunities, but first a short recap for some context. Next slide, please, Chris. So whenever we use our eyes, this is the portion of the electromagnetic spectrum that we can detect, and that provides us with all the colors we see. This swath of wavelengths from about 400 to 750 nanometers is referred to as the visible spectrum. And it's essentially the same spectrum captured by our cell phone cameras, our DSLRs, and mirrorless cameras. Such cameras are generically referred to as one-shot color cameras, or OSCs. The ASI 294 MC Pro imager is also a one-shot color camera, but specifically designed for astrophotography. Next one, please, Chris. So the other type of camera popular for astrophotography is called a monochrome imager, and it only produces grayscale images. One has to use filters with such cameras to produce a color image, whereas one-shot color cameras have either a tiny red, green, or blue filter covering every pixel in the imaging sensor, and that's called the Bayer matrix. It automatically yields a color image of whatever the camera is looking at. That's certainly convenient, but it comes at a cost. It means that only 1 out of 4 pixels captures blue light, 1 out of 4 captures reds, and 2 out of 4 captures greens. Monochrome cameras are generally more sensitive than one-shot color cameras since they don't have a Bayer matrix. And so all the camera's pixels capture whatever light you let enter based on the filter you're using. This is why monochrome cameras have traditionally been used to perform narrowband imaging, since the wavelengths of astronomical interest are very specific, and as you can see here, are only tiny slivers within the visible spectrum. You can also see that they're all bunched into blue and red portions of the blue and the red portions of the spectrum, with no real representation in the deep green or yellow portions. Next one, please, Chris. This is why we have to manually assign colors captured by narrowband filters to be either red, green, or blue when we assemble our images. This particular arrangement that you see here is called the Hubble palette. It's one of the most popular narrowband palettes. Oxygen 3 is assigned as blue, sulfur as red, and they're logical choices for this arrangement since they originate from those portions of the spectrum respectively. However, hydrogen alpha originates in the deep red and is often the strongest of the narrowband wavelengths we're interested in. But in the Hubble palette, it's mapped to the green portion of the spectrum. That makes for some interesting views of deep sky objects. Next one, please. So my narrowband view of the interior of the Eagle Nebula is an example of narrowband imaging using the Hubble palette. A full color view would show this entire scene as predominantly red. But with the color differentiation provided by the narrowband palette, a much more interesting and informative scene is produced. The different colors can actually give us clues to the composition of the nebula. Next one, please. So where does this leave us regarding the dual band filter? Well, it's similar yet different than traditional narrowband imaging. This is a full color image of M27, the Dumbbell Nebula, taken with the one-shot color ASI 294 MC Pro. The dual band filter was not used here. Next one, please. When the filter is used, this is what it gathers. The filter passes a 35 nanometer wide window of light in the blue portion of the spectrum centered around the oxygen 3 wavelength, and a 15 nanometer wide red window centered on the hydrogen alpha. You can see that these windows are wider than the narrow slits that you saw a few slides back, showing the location of those special wavelengths. The beauty of this filter is that when you use it with a one-shot color camera, the blue light captured remains as blue, and the red remains as red. There's no fiddling around that you have to do in processing to juggle blue into red or green or whatever. It is what it is. This filter has basically two slots of light that it passes, and they're blue and they're red. So when we turn the camera on the dumbbell with this filter, this is what we see. Next one, please, Chris. You can see there's an absence of green and yellow light here, causing the stars to be much dimmer than the full color view, with many now completely invisible. And in the nebula itself, contrast in the structures within is boosted due to the removal of the green and the yellow light. Next one, please. A side-by-side comparison makes these differences a bit more obvious. So in summary, the dual band filter provides an interesting introduction to narrowband imaging, especially for those of you who have experimented with one-shot color astrophotography, but have been a bit reluctant to get into the more complex filtered astrophotography required when shooting with a monochrome camera, not to mention the additional somewhat extreme expense at times. And in addition to improving contrast and visibility of deep sky nebula emission nebulas, this filter can also help to reduce the interference of moonlight or even light pollution to a degree. So I look forward to experimenting with this filter on a number of targets, especially now within, with our summer and the Milky Way being visible. There's a lot of interesting stuff to shoot up there. I'm gonna try grabbing a few things with camera lenses and the big telescope. Hopefully we'll continue having the clear skies that we've had. It's been a treat and kind of unexpected. That's it for me this month. Wishing you all many more clear skies and many sleepless nights. Cheers, and we'll see you next month.
Great. Thanks so much as usual, Paul.
You're welcome.
Okay, we'll move into the final section of the program tonight and various announcements and observing challenges. Oscar, do you want to present your own challenges to people?
Sure, why not? All right, so last month we had Messier 80, NGC 6207, Curzon 7, and Plato. Apologies to Bob for not choosing targets above his horizon.
Right, congratulations to Bob for taking on the challenge and getting one of them.
All All right, so this month, Bob's got a leg up because he's already imaged NGC 7000, but that'll be the beginner challenge for the month. That's the North America Nebula in Cygnus. Our intermediate challenge will be Able 2199, which is a galaxy cluster in Hercules. Next one, please. Our advanced challenge is IC 4954, an emission nebula in Vulpecula. And our lunar challenge is Borealis, which is a lunar impact crater on the western part of Mare Nubium on the moon. That's it for this month for the challenges. Again, NGC 7000, Able 2199, IC 4954, and the crater Borealis. Good luck to those who take on the challenges.
Great. Thanks, Oscar. And a reminder to everyone that a summary of these and this slide will be in Astronaut. So you'll be able to remember what they are and impress us next month with your results. Okay, moving into announcements. This slide may surprise a few people. Here we are in the peak of the heat of summer. And here we are talking a 2023 calendar, which is typically purchased for Christmas. But for those who remember last year, the calendars came quite late. We didn't get them until well into December. We're trying to do everything a little earlier this year. So we're now ready to accept pre-orders for the 2023 calendar. You can always purchase these online from the RASC National Office, but we sell them for a lesser price and save you the shipping costs. So by submitting a pre-order and choosing one of 4 locations in Ottawa, you'll be able to get them well before Christmas. Now, apologies, this slide says that you can order on the RASC Ottawa website. That normally would have been the case if Mick hadn't fell ill today and been unable to get to this yet. So in the next day or two, I suspect this will be on the web, and we'll send an email to everyone with a link to the order form. You can see the pricing on the right. It's actually the same as last year. We'll see how long National can hold that price. Okay, public star parties in CARP. We have 2 coming up on the calendar prior to our next meeting. So August 19th and September 2nd, as always, we have a large number of telescopes set up at the parking lot of the CARP Library, also co-located with the Diefenbunker. Great opportunity to allow the public to come and look through our telescopes. And thanks so much for Andrea for taking on the job this year of coordinating these. So this slide here shows you a bit more detail where exactly we set up in the parking lot at the library. All we can do now is hope for clear skies. Of course, for members, the Fred Lossing Observatory is open, and encourage members to get out with really 2 options. You can come and use the club's equipment, particularly the 18-inch Star Master in the Fred Lossing Observatory here in the upper image. But a lot of people come, as you see the telescope on the right, and just use the observing platforms and the power there and the nice dark skies and the camaraderie of observing with other members. So observatory is open. And as well, Gordon Webster always coordinates member-only star parties at Flow. Unfortunately, July 30th, he had to call a no-go for weather. We've got our fingers crossed for August 27th and dark skies with a new moon. And for those, though, who may have a conflict here, this is also the famous weekend of Starfest. So take your pick. I hope to see some of you at Starfest. Bit of information on the club, as each aspect of the club has someone else in charge of it. So for more information on Flow, Rick Scholes, the Flow director, and so on down the list of members you can access to obtain some of the member services. So thank you to all the organizers and speakers tonight. Especially thank you for Mick for doing all the hard work of putting all this together, and too bad that he's not feeling well and couldn't come to present it. Our audience tonight, I didn't have time to type it in while I was multitasking, but we were approaching 70 people in the meeting at some points tonight. So thanks again to the presenters. As we said at the beginning, the video of tonight's meeting, plus the presentations, observations, challenges, will be all put on the website and in Astronotes for you to access and view again. And final notice here, our next meeting 1 month from now in September. It would normally be the first Friday, but because of Labor Day long weekend and so many people being away, we'll do the usual thing and postpone it 1 week. So the second Friday of September, Friday, September 9th, will be our next meeting. We'll look forward to seeing you then. In the meantime, good night and get out and do some observing and forget about sleeping.
Thanks.